Yeah, thank you, Robert. Thank you for the introduction. I'm very happy here to share our current work on the pattern search in shape restrictions of in the additive models. This is a joint work with my advisor, Rahul Mazumdar. So as an overview, we could first introduce the problem and formulate it at the MIP, and we talk about our algorithms. And finally, we also mention some statistical properties of this problem. To start with, we have a model with response generated by the summation of function f0 as a noise term. The f0 is assumed to be to have a additive structure, which is summation of univariate functions fk. Each one is a function of the factor xk. So our goal is to estimate the function f0 based on this data. Of course, we need to make some assumptions on each univariate function. So one possible way is to assume that it satisfies certain shape restriction. For example, we can assume that fk is a increasing function, or we can also assume it's like a convex function. So this is a classical setting, and in that case, the problem can be formulated as a quadratic programming, and it can be solved efficiently. Our focus here is a bit different. So here we assume that each function fk could have a bit different possibilities of shape restriction, but we don't know exactly which one is true. So for example, we can assume that function fk is either increasing or decreasing, but we don't know exactly it's increasing or it's decreasing. So we call this as a pattern is not known. This problem has been considered by a few references, but their focus is basically on some heuristic method to do that. This is basically because that this is a hard problem. This is hard because like for each function, it could have a bit different possibility of shape restrictions. So there will be exponentially many different combinations of them. And that is the major difficulty of this problem. So to start with, we will formulate this problem into a optimization. So here, the variable uk corresponds to the function fk, and the uk lies in the union of these constraints, which means that each constraint is polyhedral, and it denotes the different possibilities of the pattern or the restrictions. And our goal is to minimize this sum of squares error. Here we also have a rich term. So this term is kind of used for to make sure that the solution can be is unique, and it also necessary for the algorithm. Note that here this constraint is actually a non-convex one, so we have to reformulate as into another formulation. So we're going to use a perspective formulation. So here we're going to introduce different copies of ukj. So here the summation of wkj corresponds to the one variable uk in the previous formulation, and here wkj lies in the polyhedral ckj, which means that it satisfies some shape restriction. And we also introduce binary variables. So by this constraint, we can see that when zkj is 0, corresponding wkj must be 0. So it can be verified that this formulation is equivalent to the previous one. So here, note that this is a polyhedral, and this constraint can be essentially transformed to as a SOC constraint. So the whole program is exactly a MI-SOCP formulation, and we could have a lot of solvers for them. But unfortunately, here, the solver doesn't work very well on this problem. We will see that in the experiments. So one of the possible reasons is that here we have too many continuous variables here. Like we have all these summation of variables, and each wkj itself is a vector. It's of dimension n. So the solvers just does not scalable for this problem scalable well. So how do we do that? So basically, we will decompose this problem into two stages. We can define the function g of z as a partial minimization with respect to the continuous variables w and g. So remember that the function h is the objective in the last formulation. So it's this objective. So once we define the function g, we can reformulate the problem in the following way, like this minimization g with these binary variables. So at a high level, our method is to use a version of cutting pillar method for problem 5. And to do that, we have to evaluate the gradient of G in each iteration. So we have to solve problem 4 to compute the gradient there. Let's look at some useful properties of function G. G is convex and continuous and differentiable on R, and its gradient can be computed once problem 4 is solved. And finally, the gradient is also uniformly bounded and uniformly Lipschitz continuous over the positive origin. So the last point is not that a trivial fact. It needs some efforts to prove, but it's also quite useful for the algorithm. We will see it later. So as promised, we will use a cutting plane method for problem 5. We will approximate function G with a piecewise linear approximation, and in each iteration, we need to solve this is a binary programming problem. So note that here, the number of variables is much smaller than the previous MI-ISOCP formulation. So we're just solving this with the IP solver. It's quite efficient. And also, as promised, we need to solve problem 4 to compute the gradient. This will be the focus of the next page. And one thing I want to emphasize here is that note that we have here, in this theorem, the gradient can only be computed at the point that all the coordinates is strictly positive. But here, we actually need the gradient at the binary point. That binary point, it will have some coordinates being 0. So how do we do that? Actually, what we're doing is to replace it by a gradient of a point that is close to Zi, that is with all these coordinates being positive, but so that the gradient can compute it. Note that we have proof that the gradient is uniformly bounded and uniformly continuous. So this approximation, the error can be bounded, and finally we will have the error can be controlled in the finally. As I mentioned, we need to solve problem 4, and here we will use the block cyclic minimization, which is quite simple algorithm, but it's also very powerful. So we will use BCM for each block WKG, and we can prove that the simple algorithm would satisfy would have a linear convergence rate, and more interestingly, this rate is not related to Z. So note that here, if we have different values of Z, the problems will be generally different, but we can prove that the linear rate is not related. We have a not related rate with respect to Z for all Z in this convex hull of the G of Xi. And of course, we have to settle the problem for the minimization of each block. And fortunately, here we have some highly efficient specialized algorithm. So for example, if you want to solve each component is increasing or decreasing, we can use the algorithm called pole adjacent evaluator algorithm, which is highly efficient. We can solve the very large n in a very few seconds. So with all of these helps, even though that BCM is used as a subproblem, it can solve this. We can solve this problem quite efficiently. And so let's look at some numerical results. So compare with our algorithm with solving the MI-ISOCP formulation, directly use Groovy. So here the SNR is the signal to noise ratio, and the gap is the upper bound, a gap between upper bound and lower bound in the cutting plane method, and the error is denote the percentage of mistakes we make in choosing the shape restrictions. So as we see that even for D equals 20, the Groupies have already been quite slow for this problem. In comparison, our algorithm is much more efficient and can solve this problem easily within 1 second. So here's some results on the larger instances. Here we try D equals 100 and N is much larger. So what is interesting in this experiment is that as we can see that as S and R get larger, we could see that time is much shorter for that problem. And more interestingly, when N is larger, the time also gets shorter. Basically, this is possibly because like the underlying problem have a favorable statistical property. So in that case, our algorithm will have better performance. And finally, I could also mention some statistical properties of this procedure. So we proved that under some mild conditions, the risk bound, which means the like kind of a distance between the true function and the estimator. So it will convergence to zero as n increases. The convergence to zero at this rate if we are doing the increasing decreasing components, and the risk will converges to zero under this rate if we do convex and K components. So different in rate is basically because the different metric entropies of the function classes in these two cases. And once we have the risk bound convergence, we could claim that we can perfectly discover or recover the shape, the true shape, as long as the risk is below a constant. So this statistics properties guarantee that the procedure we are considering is it makes sense statistically and it will have a good performance in practice. This is the end. Thank you for listening.